Okay, thank you, Matt, for your nice introduction. And thank you so much for inviting me to give a Kadanoff seminar, even from the confines of my basement. That's a great honor. And talk about this line of work, which over the years has allowed me to pick up a large list of wonderful collaborators, probably a little bit too large to go into detailed introductions. So let me just briefly introduce the 6 individuals that have mostly contributed to the recent results that I want to eventually focus on in this talk. The top row is my current and former students, Matthäus Schossler, my current student, Sumanta Bandyopadhyay and Li Chen, who have moved on to nice places and positions. And at the bottom, my dear colleagues, Zohar Nusanov and Gerardo Ortiz, who are both in this meeting, and also Mostafa Tanhagi Ahari, who is a former student of Gerardo. So I think I share with many of you a interest in quantum phases of matter, which is of course a very rewarding topic. It rewards us with great richness of interesting phenomena, but it also rewards us with a profound challenge to establish a theoretical foundation for these phenomena. And in fact, the problem can be so complex that if you ask different people, you get different answers for what it means to build such a foundation. But for the purposes of this talk, I would argue that a good way to go about this is to build it on 3 pillars, which is to come up with a correct many-body trial wave function, a microscopic wave function that captures the correct physics, a model Hamiltonian that's not crazy and that somehow stabilizes this wave function, and an effective field theory associated to that. Now I'm going to very quickly focus actually very much on the fractional quantum Hall effect. And in this field, you may know and agree that there is a very influential school of thought where you actually don't think of model Hamiltonians first, or maybe not even in a secondary manner. But I want to argue that this is actually a pity, because in this field, we have extremely beautiful model Hamiltonians that where they exist are the perfect glue in some sense between the microscopic wave function and the effective field theory. So I'll begin with what is not even a lightning review of the Hall effect. It's more like a list of historical highlights of the history of the fractional quantum Hall effect. The challenge is, of course, to explain all this plethora of plateaus of the Hall resistance that you see at different fractional filling factors, original in gallium arsenide heterostructures, nowadays in other platforms, particular involving graphene. And this became very quickly a theory of beautiful wave functions associated to famous names. First of all, Laughlin, also Jain and Halperin and Murray, Reed-Rezagi, long list. I can't be very complete here. And it started, of course, with Laughlin's insight. The insight that what's special about certain Landau level filling factors is that you can write down very special wave functions that you can only write down for these special filling factors. And that are very appealing, not only aesthetically, not only because they can be numerically argued to be good descriptions, but also because of their implications, especially for the low-lying excitations of the system. So you know, of course, that an electron added to a Laughlin 1/3 droplet doesn't behave like an elementary particle. It can decay into fractions, fractionally charged quasi-particles that also obey fractional statistics. They are anyons. And I think it's fair to say also Laughlin, to establish this, didn't just write down a ground state. What he really did is write down a class of wave functions that also includes trial states for these quasi-particle excitations, specifically quasi-hole type excitations. And this scheme rapidly got generalized along various different lines. One very successful approach to generalizing these ideas is this one, rather abstract. So Moore and Reed in 91 had this key insight that many viable quantum Hall many-body trial states are actually conformal blocks appearing naturally. They're first of all polynomials, but they are polynomials that can be identified as conformal blocks appearing in some conformal field theory. And then the trial wave function in this space diagram describes the bulk of the system. But it's natural to then associate the conformal field theory from which they come, which is a 1 + 1 dimensional conformal field theory, as the theory of the edge for the system. And then we have this wonderful scheme here where the bulk polynomial wave function is naturally associated to a conformal edge theory. And by Witten's famous 98 paper, there's a close correspondence between conformal edge theory and topological quantum field theory for the bulk of the system. So this establishes this link. It's of course very abbreviated, what I'm saying here. There's a high degree of very pleasing consistency. But nonetheless, I think one may always caution that going from a microscopic wave function at high energies to a correct, effective field theory that describes the low energy physics always involves some kind of leap of faith. And here maybe we have a lot of confidence to make this leap of faith already based on what I have said on the previous slide. But on the other hand, I want to argue that writing down a Hamiltonian that stabilizes the wave functions you're talking about may always increase one's confidence in the viability of the associated phase, especially when it's the kind of Hamiltonians that we have for many of these conformal block trial wave functions. So let me talk about Hamiltonians a little bit, because as I said, we have very beautiful Hamiltonians in this field. One shouldn't shy away from that. So for now, let me focus on the 1/3 Laughlin state, where we have the following Hamiltonian. It's equivalently known as the V1 Haldane pseudopotential, or the Trugman-Kivelson Hamiltonian. Following Trugman and Kivelson, we write down an ultra-local interaction, the Laplacian of a delta function. And because we want to be working in the lowest lambda level, because we're saying there's a strong magnetic field, we project this Hamiltonian, it's a two-body interaction, onto the lowest lambda level. So this has the great property of stabilizing the Laughlin state because it's a positive Hamiltonian. You can convince yourself, no negative eigenvalues, and it annihilates the Laughlin state. So the Laughlin state is a ground state, but it's more than that, because not only the Laughlin state is a zero energy eigenstate of this Hamiltonian, or zero mode, but really any Laughlin quasi-hole state is, and if you move a quasi-hole close to the edge, it becomes an edge excitation. More mathematically speaking, this Hamiltonian enforces the property in its zero modes that it has a zero mode must have a third order zero when two particles approach the same point, a property that obviously the Laughlin state has, but also when you multiply the Laughlin state with any symmetric polynomial in the complex coordinates of the particles in the two-dimensional space, it still has this analytic property and still is a zero mode. So you could say, I don't want to have this many ground states. Obviously, we have a lot of ground states here. This is some kind of sickness of this Hamiltonian, but in this case, it isn't. As I will shortly explain, we can switch on, if we don't like this, we can switch on a confining potential that renders the Laughlin state the exact and unique ground state of the system. And this rich zero mode space that the original Hamiltonian has actually wonderfully encodes a lot of the universal physics of the Laughlin phase. In particular, it wonderfully encodes all of the edge physics. Before I can efficiently explain that, I have to switch descriptions slightly. So let's remind ourselves that when we switch on a constant magnetic field, a single particle spectrum comes in Landau levels, and the essential degrees of freedom come in the form of the guiding center variables that the Hamiltonian doesn't depend on, and the dynamical momentum that are the sole degrees of freedom that the Hamiltonian actually depends on, leading to this large Landau level degeneracy. And often we say magnetic field is strong. The splitting is proportional, of course, to the cyclotron frequency. We assume it's very large and we can work in the lowest Landau level. So interestingly, formally, although this was by no means apparent from the wave functions I've written down, any Landau level is actually a one-dimensional lattice Hilbert space. In real space, these orbitals can be associated with roughly concentric rings around the origin of increasing angular momentum, and their analytic form is basically proportional to a power of the complex coordinate times an omnipresent Gaussian factor, which I will frequently drop in this talk. So that's why all these wave functions I have so far talked about were polynomials in the complex coordinates. That makes them live in the lowest Landau level. So suppose now I take something like the Laughlin state and actually analyze its spectral decomposition in the occupancy basis of the lowest Landau level. So then it's a formal superposition of these occupancy eigenstates. This is one example. And on the surface, the structure of the amplitudes that appear in this superposition is very messy and complicated. However, it's become apparent in recent years that it's not entirely useless to study this structure. Already in the mid-90s, Rizayi and Haldane made this observation that while it's a complicated structure, there's something interesting you can say about it. There is a special basis state in this called the root partition, very regular, 1, 0, 0, 1, 0, 0, such that all the other basis states appearing with non-zero coefficients have the property that they can be obtained from this root partition by inward squeezing processes. An inward squeezing process is one where you take a pair of particles and move the pair inward while conserving its angular momentum. So while it's still a complicated structure, it also implies that many basis states don't actually appear, have zero coefficient. For example, the one that I've written at the top here couldn't actually appear. It cannot be obtained from this root partition by an inward squeezing process. And so this interesting observation is not only true for the Laughlin 1/3 state, it's certainly also true for the bosonic Laughlin 1/2 state. So in the 90s, I think this observation was limited to Laughlin type states, but in the meantime, we know it's true for many other interesting quantum Hall states. For example, the Moreed state at filling factor 1 is another state for bosons. So for bosons, of course, the root partition could have higher occupancies. This squeezing picture also applies, was pointed out by Bernewig and Haldane in 2008, but there's also other ways in which you can attach fractional quantum Hall states to these simple patterns, for example, by taking the thin cylinder or thin torus limits. So the idea is this: start with the disk geometry. So I have a, let's say, Laughlin state that's formally a droplet occupying a disk. Then you poke a hole in the middle, you deform it into a cylinder. All this can formally be done. You can have a Laughlin state on the cylinder, which, if the cylinder is thick, has exactly the same local correlations as the Laughlin state in the sphere or on the disk geometry. But if you now take the thin cylinder limit, the lowest Landau orbitals become very well spaced in that limit. And the natural limit of the Laughlin state, when you make the cylinder thin, is actually that root partition. So the Laughlin state has a very simple limit in that sense. And while this is certainly cute for the Laughlin state, I will argue that the Laughlin state, of course, can be understood in many different ways through many different approaches. But I argue that these simple patterns, which we think of as a kind of DNA for the underlying quantum Hall state, they contain so much useful information that they can become an essential tool when you study more complicated quantum Hall states, in particular their Hamiltonians. So what's also important to point out is that these observations are not limited to the incompressible ground states, but also they apply to the quasi-Hall type excitations that are also zero modes of the parent Hamiltonian that I've discussed. So for example, a state of one quasi-Hall inserted into a delocalized state such that it has a well-defined angular momentum, both on the cylinder or the sphere, it is associated to a root partition that goes like 1, 0, 0, 1, 0, 0, but has an additional 0 squeezed in. So it's basically a domain wall. Incidentally, one that carries naturally the correct fractional charge of 1/3. And one can establish, and I will talk about that in some detail, a one-to-one correspondence between all the zero modes of the parent Hamiltonian and simple patterns that satisfy what's been coined a generalized Pauli principle. For the case of the Laughlin state, it's a Pauli principle that says, Pauli-like principle that says no more than one particle in any 3 adjacent sites. And these partitions that satisfy this principle, this combinatorial rule, they are in one-to-one correspondence with zero modes of this parent Hamiltonian. So it's an organization principle for all the zero modes, and I can now explain how these zero modes therefore encode the edge physics. So let's switch on this Hamiltonian. The Laughlin state is a zero mode. There is many more zero modes at higher up angular momenta, but at the lowest angular momentum where there exists a zero mode, that is the Laughlin state, and it's the unique zero mode at this angular momentum. So now I switch on a confining potential, which can just be taken to be a potential that's proportional to angular momentum. So if I switch on an additional potential proportional to angular momentum, now this renders the Laughlin state the unique ground state, and it's also a very natural confining potential. Morally speaking, it's just a quadratic potential in real space. So now how it affects different zero modes can be worked out from the root partition, because the root partition encodes faithfully the angular momentum of the state. So this is the root partition of the Laughlin state. It is the unique, densest, lowest angular momentum root partition that you can form. Now you can think of what if I want to make a delta L equals 1 excitation that also conforms to this combinatorial principle, delta L as measured with respect to the Laughlin state itself. There's only one way you can do that, because without violating the generalized Pauli principle, you can only take the outmost particle and move it outward. Whereas for delta L equals 4, you have many, already quite a few ways to generate viable partitions. And so you can keep counting at given angular momentum how many zero modes there are. But if you think about this, the Laughlin state, the generalized Pauli principle is really simple. It just says really that between any two occupied states in the root partition, there must be at least two unoccupied states. If I don't care about these two unoccupied states, I just squeeze them out. You see that the counting you are doing is just the mode counting in a single branch of chiral fermions, which you can, of course, bosonize if you want to. And this is, to me, the most efficient way to see that the mode counting of zero modes in the Laughlin state parent Hamiltonian, although it's a quite simple example, is in one-to-one correspondence with the mode counting of its edge conformal field theory. So whenever a Hamiltonian satisfies this paradigm, there's many zero modes, and their counting at given angular momentum agrees with the mode counting in some associated conformal edge theory, I say this Hamiltonian satisfies a zero mode paradigm. And so you can very easily appreciate that that's true for the Laughlin state and its Hamiltonian. There's other ways to show the same thing. So Mike Stone already showed the same counting correspondence in the year 1990. But you have to know your Schur polynomials, and then you can do it. But I think it's the most efficient way to do this counting for the Laughlin state already in terms of these patterns. And of course, it quickly gets more complicated once we get into more complex quantum Hall states. But we have many examples. This is a very partial list. I just put on this slide whatever I could fit of interesting quantum Hall trial wave functions that conform to this paradigm. They are, these examples are all conformal of conformal block type. There is a parent Hamiltonian such that there are lots of zero modes. They're counting at given angular momentum is a one-to-one correspondence with the counting in an associated edge conformal field theory. And also all these zero modes can be shown to be in one-to-one correspondence with some simple pattern satisfying a simple combinatorial rule. So this is a slightly different list of states for which Bernabig and Haldane established this in 2008. For all these states, and actually many more, we have as a reasonably simple combinatorial rule, a generalized Pauli principle, such that mode counting is equivalent to counting all states satisfying this rule. So hopefully I've convinced you that actually this existence of such wonderfully solvable Hamiltonian that contains so much information in their zero mode space allows us to tread this, make this leap of faith with quite some confidence, treading on rather solid ground here. But so far, keep in mind, I've only been speaking about a large class, but still a special class of wave functions that are of this conformal block type, and that's way not exhaustive. For the second part of my talk, I want to talk about another very rich class of states, so-called parton quantum Hall states. And perhaps the biggest omission of my talk so far is actually what's known as Jain composite fermion states, some of the most important and successful trial wave functions in this field. And so the idea is, of course, that the correct way to think about many quantum Hall states and essentially everything that's relevant to the lowest Landau level in gallium arsenide, is to think not of bare electrons, but so-called composite fermions, which are bare electrons that absorb an integer amount of flux quanta. So Jain came up not only with this picture, but also with wave functions that correspond to it. So this is the Jain 2/5 state. Apart from the Laughlin state, it's probably the most important and most stable quantum Hall state that we know. And it is a different kind of animal though. So it has this Laughlin-Jastrow factor, but it's multiplied with a Slater determinant that fills 2 Landau levels. So it's not a state anymore that lives in the lowest Landau level. We can get around that, and we frequently do by taking the state and projecting onto the lowest Landau level, which makes this wave function actually rather more complicated. For the purposes of this talk, I will not project. I will work with the unprojected Jain states. And for these, we have actually recently constructed, for this entire class of states, we've constructed a set of parent Hamiltonians that are 2-body interactions, not only stabilizing the incompressible Jain states, but also a set of 0 modes that again satisfies this paradigm that's in 1-to-1 correspondence with the edge theory that's expected for the Jain states. I don't have time to explain all of that, but what I do want to explain is what happens to Pauli-like principles when looking at these states and all the associated edge excitation. So more explicitly, this is what the state is. We have now Z and Z bar appearing in the wave function. So it doesn't live in the lowest Landau level. First thing we should agree on is how do we associate, even formally, a root state to this fairly complicated wave function. So we actually go with following working definition. I expand this state in a occupation number basis, and then I keep only those states that are not obtainable from other states also appearing in the decomposition by these inward squeezing processes. So the root level, the root state, is defined as all the Slater determinants appearing in the spectral decomposition that cannot be obtained from others by inward squeezing. And then we find what the root state of this wave function is. This is an example of a Slater determinant that appears in here and cannot be obtained from others by inward squeezing. So now we have 2 Landau levels. We signify that by sort of attaching a pseudospin to our fermions, a pseudospin that really encodes the Landau level that they're in, the lowest or first excited Landau level. And I think of these orbitals with given angular momentum, and either for spin down, lowest Landau level, or spin up, first excited Landau level. This would be one Slater determinant that is contributing to the root level. But it's not the only one. Really, when you calculate the root state by this definition of this wave function, you get a product of singlets. So this is the correct root state if I do it according to this rule. And we established for the Jain state a Pauli-like principle that we call an entangled Pauli principle, because you can see at root level, entanglement is now possible and quite important. The principle that root states are subject to is that there's no double occupancies, no nearest neighbor occupancies. And if there's next nearest neighbors, they must form a singlet in this pseudospin basis. So if you think about it, that very naturally, even if you didn't know anything else, leads to a densest filling factor of 2/5, because any root level occupied site can have only one next nearest neighbor, with which it then must form a singlet. And by the monogamy of entanglement, there can't be any other next nearest neighbor. So the next one has to keep a distance 2, and so on and so forth. That naturally leads to a densest pattern at filling factor 2/5. And in general, we can write down all root states that conform to this entangled Pauli principle. At less dense filling factors, there could be isolated spins which are unconstrained. You can show that if you count all these root states at given angular momentum, again, you find that it agrees perfectly with the edge theory that's expected of this state, which has 2 branches of chiral bosons. So there's a lot more interesting things to be said about composite fermion states. Unfortunately, I don't have time for that. I just want to use them as a stepping stone into a direction where you go away from these conformal block trial states and actually construct interesting and complex mixed lambda level wave functions. So the main object for the rest of this talk is what's actually known as the Jain 2-2-1 state, which is like the 2/5 state, but I have moved the exponent 2 from the Laughlin-Jastow factor to the Slater determinant. And because that now makes higher powers of Z bar possible, this state now actually lives in 3 lambda levels. Now, what happens to the entangled Pauli principle? The shift in exponent actually changes the filling factor to a denser value of 1/2. And the root state, defined as before, is still a product of singlets, but it's now a pseudo-spin 1 degree of freedom, because we have 3 lambda levels in this game now. There is an associated parent Hamiltonian that I will tell you what it is on one of the next few slides. And we can derive for all of its 0 modes, again, an entangled Pauli principle, very similar, but interestingly different compared to the Jain 2/5 state. So this one says no double occupancies, nearest neighbors must form a singlet, and next nearest neighbors must form a singlet or triplet, but cannot be spin 2. So, and this last rule makes all the difference, because actually the densest filling factor at which you can write down a root state satisfying all these rules, it is 1/2, but this is not the only possibility. There's another way in which you can achieve this filling factor, where you can have a occupied site, occupy its next nearest neighbor, and then you can keep actually going and construct a string of next nearest neighbors that are subject to this 3rd rule. And it's not obvious that this constraint can be satisfied for arbitrarily long strings, but it is known in the literature because it's actually the constraint that defines ground states of the AKLT spin chain. So formally, these types of root states have AKLT entanglement, where you have a string of occupied sites, formally having a pseudo-spin 1, that are entangled as is the ground state of an AKLT spin chain. Related to the fact that we have these 2 inequivalent densest root partitions, this is actually a non-abelian quantum Hall state, and I will explain this later in the talk. This is actually—
Can I ask one question on that?
Yeah.
In this picture now, should each of these positions be thought of having a full spin 1, up, down, and 0, or should each of these positions be thought of as a spin 1/2? Like in the AKLT, where you can kind of think of virtual spin 1/2s.
Yeah, that's a great comment. They should be thought of as spin 1. it is true that I'm glossing over the fact that not only can you satisfy this constraint, but you can satisfy it in 4 different ways, because there is associated to the edge, of course, in the AKLT chain, a spin 1/2 degree of freedom. So for now, I'd like to gloss over that, but we can talk about it later or in the end of the talk. But you could think of what I draw here, that represents a spin 1. And this is a string of spin 1s that are in an AKLT ground state.
Okay. All right, thanks.
All right. And the first picture has nothing to do with AKLT. It looks a little bit suggestive, but this one, these are also spin 1s. They have nothing to do. They just form dimers, pairs of singlets. Okay. So before I continue, let me point out that this is actually just a representative of an incredibly rich class of states where you form products of Slater determinants. So this can be read as, a product of obviously two Slater determinants with 2 Landau levels filled. The lone Jastrow factor in the beginning is also a determinant. It's a van der Monde determinant, formally filling a single Landau level. So it's a product of 3 Slater determinants. And general states of this type are what is called parton states, a very rich class of states that was already studied by Jain and Xiaogang Wen in the early 90s, except this Hamiltonian business that I'll talk about is fairly recent development. So now let's think about constructing a parent Hamiltonian for these animals. So obviously there is still a nice analytic property, which is when you move 2 particles, any pair of particles to the same point, the wave function obviously has a 3rd order 0, because every Slater determinant becomes individually 0. So that sounds similar to the Laughlin 1/3 state. So why don't I just try the same Hamiltonian, except now I'm projecting onto the lowest 3 Landau levels. So this is what Wu, Shi, and Jain proposed 3 years ago. They studied this Hamiltonian. And you can see immediately the Jain 2-to-1 state is a 0 mode of that. It's again a positive Hamiltonian. Any 0 mode is a ground state, but in fact, any product of 3 Slater determinants, you can make arbitrary excitations in any of these 3 Slater determinants. That would still be a 0 mode of this Hamiltonian. So what we have is a Hamiltonian that enforces in its 0 mode this clustering property that we have 3rd order zeros. The Jain 2-to-1 state satisfies this. All products of 3 Slater determinants satisfy this. So could we call it A then? And the answer is no, because by itself, these observations don't actually lead to anywhere conclusive yet. So we need to know that there is no other 0 modes than those. We need to know that the 2-to-1 state is the densest 0 mode if we want to play the similar games, and we need to have a control of the complete counting of 0 modes. So we want to make sure we know all of the 0 modes, and there are no others than what I've listed here. So in particular, when we again switch on this confining potential, we want to make sure that the 2-to-1 state is the densest appearing at the beginning. And on top of that, we can build our edge physics from the known 0 modes. So this is actually, you could say, similar analogous problem exists for the Laughlin state. It was easy to solve there. It should be easy again. But that is actually quite a deceptive notion, I would say. Before I explain you why, one more physical observation about this Hamiltonian. It still has no kinetic energy. It's purely a 2-body interaction, which sounds like an undesirable property. So we're making artificially you might think, the first 3 Landau level are degenerate by not giving them any distinct kinetic energy. That looks like an undesirable feature, but it's not necessarily the case because, as also pointed out in this paper, this naturally happens in tri-layer graphene if you have the right stacking. So there you can have a situation where naturally 3 Landau levels are exactly degenerate, which is why I would say this is an entirely not crazy local two-body interaction. So it's actually quite a nice Hamiltonian. So that should be reason enough to study its properties. So now back to the statement that we want to show. We would like to establish that all the zero modes of this Hamiltonian are given by the Jain 2-to-1 state as the densest or lowest angular momentum state, that is a zero mode, and states of the form where we keep the Laughlin-Jastrow factor, but allow for a product of any 2 selected determinants. They don't have to look like that. They can have holes anywhere. We would like to show that this set linearly generates all zero modes. Sounds like a reasonable conjecture. It's not so easy to prove that. To appreciate that, we can, for example, take the point of view that often all you need to do is find a mathematical friend, and the still should also mention that if we have achieved this, we're not quite done yet, because inconveniently, this set of states is still over-complete. So it doesn't still, in any straightforward way, lend itself to zero mode counting. But okay, so let's find a mathematical friend. We could try to formulate the claim in slightly more mathematical terms, where the problem is basically find all polynomials in variables z1, zn, but also z1 bar, zn bar, with the requisite anti-symmetry, at most second order in any of the z bar I, because we're living in at most 3 Landau levels, and third order zeros as any 2 particles go to the same point. And we want to show that they satisfy these properties. Again, you could say, well, we've solved a similar problem for the Laughlin state, so how much more difficult can it be? Actually, it's a lot more difficult, because if I compare this to the completely analogous problem for the Laughlin state, here is what you modify. So the Laughlin state lives in the lowest Landau level only. There's no z bar dependence. There's no annoying constraint on the degree of the individual coordinates. And as a result, it becomes a matter of simple divisibility. The zero mode condition is just that your polynomial is divisible by zi minus zj to the 3rd power for any pair ij. And just by divisibility in polynomial rings, the whole wave function must then be divisible by the polynomial associated with the Laughlin state. That immediately makes the Laughlin state the unique densest or smallest degree such polynomial. And it's very simple math by comparison. And however, for the problem at hand, we have a lot of interesting and quite annoying additional constraints. Most importantly, for the 2-to-1 parton state, the zero mode condition for any pair can be satisfied in multiple ways. You don't have to be proportional to zi minus zj cubed. There's other ways to satisfy the 3rd order zero, and that makes this problem a lot harder. So as a result, we actually didn't get much help from our mathematical friends, and we had to go down different roads. We found our own proof strategy that actually largely eschews polynomial language altogether. So we constructed the following logic, which actually works Very well. So we have a Hamiltonian, it's positive, semi-definite, and we can prove that any zero mode is subject to a entangled Pauli principle at root level. So this you can actually prove just by writing down the Hamiltonian. Then if you think this through, and I'll be more explicit on my next slide, this actually sets an upper bound to all the zero modes that can exist at any given angular momentum, because it can be at most as many as there are root states that satisfy the entangled Pauli principle. And if on top of that, you have shown that for every root state that satisfies this principle, there exists a zero mode whose root state it is, then you have actually proven that there is a one-to-one correspondence between patterns satisfying entangled Pauli principle and zero modes. And so you have proven in particular that you have found all zero modes. So this is the program that we carried out so far for the Jain 2-to-1 state. And I cannot explain this in too great detail, but let's ponder the question why this is the unique ground state. So from the Hamiltonian that I showed you, we have derived this entangled Pauli principle. And there are two densest patterns, as I've shown you. There are actually subtleties I glossed over. So these patterns are completely equivalent on the torus, but on the disk geometry, there are interesting boundary conditions which render them slightly inequivalent in any case, without going into that. The first pattern seems to have lower angular momentum. So it's actually, even after careful analysis, it's the unique lowest angular momentum root state consistent with this entangled Pauli principle. So that immediately tells you there can't be any zero modes at lower angular momentum. They would just violate our theorem because there's no root states that can conform to this principle at lower angular momentum. At the lowest angular momentum, you show that the 2-to-1 state actually has precisely this angular momentum, as it is actually dominated, like I told you, by this root pattern. At this angular momentum, it has to be the unique zero mode. Because if there were any other zero mode, it would also have to be dominated by this root pattern, according to our theorem. But if you had two zero modes, both dominated by this root pattern, you could make a linear combination that has zero overlap with this root pattern. And then you have a zero mode that violates our theorem, so it can't happen. So from this line of reasoning, you establish the 2-to-1 state as the unique densest zero mode of its parent Hamiltonian. And you can generalize this line of argument to all the higher up angular momentum as well. You find a parton-like state for every possible root pattern that's subject to these combinatorial principles. And that shows that the bound given by the entangled Pauli principle on the zero mode space dimension is actually saturated. So there is a basis. These states are overcomplete, but you can pick a basis in one-to-one correspondence with permissible root states. And so now zero mode counting is actually under control. This slide I'm just flashing to show you what kind of games you play to do the zero mode counting by hand now in terms of these patterns. This is precisely, these little spins here relate to Matt's observation that 1010 strings are subject to AKLT entanglement, and they actually come fourfold degenerate. So they have dangling boundary spins 1/2. That's just one of the rules of this game. And so you can you can count zero modes at given angular momentum. When we do that, we obtain the following table. We didn't attempt to get a formula for arbitrary delta L, although I think it may be possible, but you get very non-trivial numbers already for delta L up to 4, and they beautifully agree with the edge theory that Xiaogang Wen already proposed in 91. He somehow got it right, but we can add to that now that this also fits like a glove with the parent Hamiltonian written down by Jain and collaborators in terms of the zero mode counting. And notice that although we only did go to delta L equals 4, this applies independently of particle number. So this applies for any large particle number. So it's much more than you could demonstrate numerically for this parent Hamiltonian, especially because numerics are also quite challenging to do in 3 Landau levels. So now one more observation on this strategy that I've been going about. One interesting aspect of it is that if you've been studying these Hamiltonians for some time, it's actually interesting that we can do almost everything, and in some cases everything, without ever mentioning polynomials or first quantized wave functions, which is very surprising because if you take this parent Hamiltonian and you write it out in the occupation number basis, write it out in second quantized form, it becomes a rather strange animal, a rather interesting beast. It's a pair hopping Hamiltonian in this lattice. And here I'm suggesting some boundary condition that we have on the sphere, in the disk geometry in particular. And its center of mass or angular momentum conserving pair hopping in this lattice. And it's quite tough to see if you present the Hamiltonian in this way that it has any zero modes at all. So it's formally, however, we know that it does. So it's a frustration-free lattice Hamiltonian. It's the sum of positive operators. If you have a zero mode, it's necessarily the ground state of each of these operators in this large sum. So it's a frustration-free lattice Hamiltonian. But even if you reduce everything down to the lowest Landau level, in which this just becomes the parent Hamiltonian of the Laughlin state, it's hard to see that it has any zero modes at all, even though we found ways to study all the properties of this Hamiltonian without ever referencing polynomials, at least in the Laughlin case and some others. This observation is certainly related to the facts. So we have, of course, many frustration-free lattice models in the literature, but they tend to be a finite range if we can solve them. This is formally not a finite range. The pair hopping range may decay exponentially at large distance, but formally it's non-zero at any distance, which is what makes this relatively hard to study on the surface. But it's related to the fact that became relatively recently appreciated that many interesting quantum Hall states can be presented as matrix product states. And again, there's many nice, cute lattice models in the literature that are frustration-free. The ground state is a simultaneous ground state of all the many terms in the Hamiltonian, and that have an associated matrix product ground states. But usually the examples are such that the interaction range is strictly finite, and the bond dimension of the matrix product state is also finite. So here we have an example where you have an infinite range positive Hamiltonian, lattice Hamiltonian. It's frustration-free, and associated to that, there is an infinite bond dimension matrix product ground state. In some cases, we have been able to extract all the properties of the Hamiltonian, in particular the fact that there exists a frustration-free parent Hamiltonian starting with the infinite one-dimension matrix product state, which is actually still a published work by my student Matthäus Schossler. But I think it suggests itself, it suggests that that there could be sort of a Hamiltonian building framework for infinite dimension matrix product states more generally. So the connection between matrix product states and frustration-free lattice Hamiltonians is of course very well understood in the finite case, but I think it's very mysterious still in this infinite setting. Last thing I wanted to show, and I hope it's okay if I go like 3 minutes over time, is why is the Jain 2-2-1 state a non-abelian quantum Hall state? And related to these root state patterns. So let's consider a situation where you have 4 hole-like quasiparticles. They would be associated to a root string pattern with actually 4 domain walls between the 2 types of densest root patterns, the, let's say, dimer pattern and the AKLT pattern. And these domain walls actually carry a fractional charge 1/4, which is also the expected fractional charge for quasi-particles in this state. So now let's contemplate exchanging these 2 quasi-holes in the middle. What can happen as a result is that you transition into a state with a slightly different root pattern that has in particular the dimer string in the middle between these 2 quasi-holes shifted. So this is now shifted. And notice also that the pattern didn't change for any orbitals to the right or to the left, orbitals which didn't participate in the exchange, which make sense that the root pattern shouldn't be affected there. So on the other hand, if you contemplate what could happen if I exchange these, or actually before I go on, you may complain, of course, that as a result of this proposed transition, the domain wall has slightly changed location. So you could say, well, how can this be a locally undistinguishable state if I shift my domain wall positions? That's actually okay, because these domain walls shouldn't be thought of as entirely localized. In Landau level physics, there's actually an uncertainty principle between the X and the Y position. So to localize anything in the Y direction, you have to delocalize somewhat in the X direction, which is why these domain walls must actually somewhat be delocalized. So it's okay if I shift the domain wall position. In some sense, those domain wall positions are only well-defined modulo 4. Now you can contemplate what happens if you braid the 2 quasi-holes to the left. In this case, you cannot transition in the sense that you cannot replace this string except for the domain wall position, which is anyway fluctuating. You cannot replace this with any other types of string. The surrounding dimer strings give rise to a boundary condition that if you want to have charge 1/4 domain walls, this AKLT string cannot be replaced. However, since domain wall position is well-defined modulo 4, the length of this string, of this AKLT string, is well-defined modulo 2. So it could have an even or odd number of particles which is a property that also cannot change as a result of the exchange. And so the phase picked up can actually depend on the even oddness of this AKLT string. So basically, these rules can be organized in a Bratelli type of diagram, where every time you have a AKLT string and seek its right neighbor, you have the choice between two different types of dimer strings. But every time you have a dimer string, its right neighbor is uniquely determined, a uniquely determined AKLT pattern. So if you organize these choices into a Bratelli diagram where from the AKLT string, you can go either up or down and then only back into one uniquely defined AKLT string, you can associate all these patterns with topological sectors whose number is just the number of paths through this Bratelli diagram. So sorry if this is very sketchy. All I want to say is that there is a nice consistent way to derive from these observations all the amplitudes and phases for the allowed transitions. And what you get, although it's not free of assumptions, there are of course some assumptions that I'm making, is nicely consistent with field theory methods. Specifically, the rules I've sketched here are perfectly consistent with Majorana statistics. You basically associate a Majorana with each domain wall, then you pair domain walls about a AKLT string into a fermion. You say the fermion is occupied if the number of particles in the string is odd and otherwise it's unoccupied. Then these rules are perfectly consistent with Majorana statistics. There's also an overall abelian phase, which is not totally fixed by our method, but it is constrained. So sorry for going a little bit over time with this. Let me just flash my conclusions and maybe look forward to some discussion.
All right, thanks, Alex. Why don't we maybe have a couple short questions now and then we can take a break. So yeah, feel free, anybody.
Can I ask a question?
Yeah, sure, Michael.
Hi, yeah, I was just wondering what is known about what types of states can be realized with these kinds of model Hamiltonians? I mean, for example, I assume you can't get states that where you have counter-propagating edge modes. Is that true?
Yeah, that would have been my answer if you hadn't said it already. It's true, there is, of course, severe limitation when you have counter-propagating edge modes. You can maybe get away by starting with models and then taking their particle hole conjugates, but it is probably, I haven't tried to exhaust possibilities, but so far this is largely limited indeed to states with co-propagating edge modes, and it is not, however, limited to conformal block states.
But even some states with co-propagating edge modes might be challenging, I imagine. Like that's sort of what I'm wondering. Is there anything you know about, like, for example, a strong pairing state, or I don't know, can you get that state?
That's true. So there's certainly still a wealth of quantum Hall states where we don't know anything about Hamiltonians. And yeah, I don't have the answer to that if it's fundamentally, of course, when you can't find a parent Hamiltonian to any particular state, that doesn't mean you can't find one for something that's in the same phase. My feeling is the class of states that admit parent Hamiltonians is larger than appreciated. So it should, and not only parent Hamiltonians, but ones that conform to this zero mode paradigm where you have faithful edge counting. It should include all states with, let's say, co-propagating modes that can be represented as matrix product states. And it certainly includes probably most of these parton states, but I really don't know at the moment where the limits are beyond beyond those difficulties with counter propagating modes.
I see. All right. Thank you.
Thanks.
Okay, any other quick questions or? I also have one more general question. Is there a way to see from these constructions if there's any CFTs that are probably not consistent with the edge of one of these type of Hamiltonians?
Well, there are many constraints on the CFTs that are known in the literature. So they have to be unitary, for example. They have to have in a certain primary field that can qualify as the electron operator. It has to be local with respect to all other fields. So there are many constraints, certainly well known on these CFTs, that for which in particular you can play this game of constructing conformal block wave functions. And more, I mean, of course, generally they have to be unitary also.
Okay, the reason I'm asking is I heard from Andrea Capelli talking about he has this W infinity approach to quantum Hall states, and he told me something about that requiring the edge CFT to have a representation of W infinity gave some constraints on what CFTs could actually be the, appear at the boundary of a quantum Hall state.
There are many constraints.
Okay, I guess I was wondering if because this also gave some way to extract CFT data if it offered other constraints or something like that.
Yeah, it is. It's tempting to try to turn this game around and study these questions so well with other methods that in the end you can learn something about CFT. That would be perhaps the ultimate goal.
All right, so maybe it's a good time to take a break. So I'll turn off the recording.